The second phenomenon that scientists were looking at in the early 1900s and late 1800s was this phenomenon called the photoelectric effect. Let's set it up. Again, this is going to involve light, photo meaning light, and electricity in this case. So what scientists were observing is that if they had a piece of metal and they shone light on it, it would sometimes kick off. So we have light coming in, and generally this is UV light, though it can be visible depending on the metal you're looking at. When it hit the metal, electrons would come off of the metal. It would kick off electrons. And you could measure that by measuring the electrons conducting electricity and making a current in a measuring device you have over here. So somewhere over here, you have a way to measure the electrons and how fast they're going. So you can both measure how many electrons you're getting and the speed at which they're going. Or you can measure their kinetic energy, right? Kinetic energy being the energy of motion we've talked about. So there's some device here. We're not going to go into the details of that device. But for us, it's sufficient that we understand sort of this picture. If we shine light, right, which we now know comes in these little chunks, like that's what we'll talk about in a second. If we shine light on a metal, it will sometimes make electrons come off of that metal, and then we can measure how fast they're going. But again, classical physics couldn't explain how this worked, or the properties that it had. So through careful observation, scientists observed that for a particular metal, it has a threshold frequency. Or we sometimes call it the work function of the metal. And if the light is below that threshold frequency, there are no photons that come. And if the light is above that threshold frequency, then we do there are no electrons that come off of the metal. And if it's above that threshold frequency, so let's sort of represent this graphically. So if we plot like number of electrons along the y-axis and frequency along the x-axis, there's some value of the threshold frequency where anything below that you get 0, 0, 0, 0. So this is a plot where you get 0 electrons that come off, and then once you get past a certain point, you will get electrons. And how much light you put in will tell you how many electrons you get. So there's some threshold at which we get what are called photoelectrons. These are the electrons that are being ejected from the metal. Okay, so classical physics couldn't explain why it would matter, why it would depend on, and this value of the threshold frequency of the work function is different from metal to metal. So when we call it the work function, we give it the symbol phi, yet another Greek letter, and this is just equal to h, Planck's constant that we talked about in the last video, times that threshold frequency. The threshold frequency we call nu with a 0, just to indicate that's the 0, like that's the minimum amount of the value of the frequency that actually produces photoelectrons. So if we measure the speed of the electrons, we also observe something interesting, that we can write this equation. We can say, well, the kinetic energy of the electrons, based on observations, is equal to h times the frequency of the light that's coming in. So this is the frequency of the incoming light, minus h times the threshold frequency. So the extra energy shows up in the electrons. So we have some energy coming in from the incoming light, and this is again the threshold frequency. So what's going on here? What was the eventual explanation of this? Well, one thing I always find interesting about this is that Albert Einstein, who's very famous for E equals mc squared and all that, is actually the one who explained this phenomenon of what's going on with the photoelectric effect, looking at what was going on with Planck as well. And this is actually, he won his Nobel Prize for this work, not for the E equals mc squared and relativity and all of that. Kind of a fun fact of history. So what he's more famous for is not what he won his Nobel Prize for. But this was also really important, and he deserved a Nobel Prize for this explanation as well. So what's going on here is we're again seeing the idea of the quantum showing up, but this time for the light. And what the photoelectric effect tells us is that light is quantized as well. So, not just the black body, that the energy inside of your black body has specific amounts, but light is quantized and comes in little packets. So we have this idea of what we call packets of light, or if you're familiar with the term, this is what we call photons. So light itself can only come in distinct amounts of energy. And so the light that individual light photon has to have enough energy to overcome some energy that's holding the electron onto the metal. So if we sort of picture this on an atomic level, we have the positive charges of the nucleus, and there's some electrons sort of loosely associated with this. And if we give those electrons enough energy, they can leave. But you have to have sufficient energy to overcome the attraction between the positive and negative charges here. And that amount of energy you need is the work function, this phi. So this incoming light, even if you have a lot of it, if each individual photon doesn't have enough energy, if each individual packet, you're not going to have enough light to kick off the electron and see the photoelectric effect. And also what we see is that the amount of kinetic energy that the electron has afterwards is basically all the leftover energy from the photon. So most of it goes into this electron moving, and that leftover energy goes into kinetic energy. And so what was brilliant about Einstein is he realized that this was the same idea that Planck used, right? It also applied to the light as well as to the matter in the black body. And he even, if you work it out and look at the data, this value of h, this Planck's constant, is the same in both experiments, indicating that we have the same phenomenon happening here. So this was another experimental evidence that scientists had to work through and figure out to show that this idea of quantum, what we call quantum mechanics, is what explains what's happening on the molecular level. And so these experiments with light really showed us and started to show us that there was something different happening than we were used to and had learned in classical physics, underlying all of what's going on with the electrons in atoms. And so we're going to explore that more in this chapter, but this is sort of the foundation. This is what told us, these experiments are what told us that that scientists need to look deeper, and gave us the idea of this quantization of energy, that energy comes in distinct packets.